This conference will now be recorded.
Hi, good evening, ladies and gents, and welcome to the last meeting for the year for the Cheshire and North Wales PWI section, or at least of the 2021 year. We've got a bursting programme ready to go again from September, when we hope to be able to run these meetings in person at Crewe and online as well. But for now, as you're aware, we're online. And this evening we've got the first of our young professionals events, which is a real great opportunity for 4 young professionals in the industry to talk about a bit of what they've done in their careers to date. So I'm really glad to welcome Lilian, Ateng, Fahad, Munir, Ratchford and Heather Campbell, who are from Engaged and Network Rail. They're graduates and apprentices, and they'll each introduce themselves as we go. But what we've got, the format is 4 15-minute presentations and then a Q&A at the end. So you can either make a note of your questions and ask them, or you're more than welcome to post them in the chat function as we go, and I can ask them of the panel at the end. So yeah, welcome young professionals, and welcome to all of our guests as well. So yeah, Lilian, would you like to start?
Yes, I would. Good afternoon, everybody. My name is Lilian and I am a graduate civil engineer. And today I'm going to be talking about the risk level of earthworks along the railway and how Network Rail is using this information. Next slide, please. So firstly, what is an earthwork? Well, an earthwork is actually just a man-made bank of soil, and in Network Rail is most commonly used earthwork is an embankment, and it is used to support the railway. But outside of the transportation sector, embankments can also be used as flood defences, especially near rivers and towns. But its strength and durability of an embankment, it can be affected by weather. Next slide, please. Weather can heavily influence the railway, especially one of the biggest types of weather most common types of weather in the UK, the rain. And this is very evident due to climate change. And this is a major issue that the railway needs to adapt to. Rain can affect the strength of the cutting, which can then cause debris to fall onto the track. And when debris is on a track, it can lead to severe delays, which damages the reputation of public transport and also the reputation of Network Rail as a whole. Next slide, please. As you can see, due to heavy rain, various earthworks have been affected. For example, in the West Highland Line in Scotland, 81 millimeters of rain, it fell within 4 hours, and this caused an embankment to fail. Then again, in Stonehaven, a rock cutting, it failed after 52 millimeters of rain fell in 3 hours. Next slide, please. Then when we head into England, there was also very heavy rainfall within 1 hour at Whitmore. And then when we travel towards Watford, 50 millimeters of rain fell within 4 hours. And this caused the tunnel portal cutting made out of chalk to fail. This is showing us that regardless of the soil type, water is an important issue. The main similarity that I have shown to you with all these examples is that they happen to be within dry areas. And dry areas mean that rainfall is typically low in those regions. So these failures were very surprising. So now you're probably thinking, what is Network Rail doing about this? Next slide, please. So what Network Rail is doing about this is that we're learning from our mistakes. As these mistakes and failures, they definitely could have been avoided by having a warning system. And this has been pushed, and it's now started the development of the Convecting Alerting Tool, or CAT for short. It keeps track of the rainfall in the area, and it then will send out a threshold message to the engineers in the area about what could happen, whether that could be a mudslide or debris possibly landing onto the train tracks. So by using CAT, Network Rail can further understand the risk levels of an area. Next slide, please. So why is the risk level so important? Well, at Network Rail, safety is our main priority. Our main goal is to ensure everybody, including you and me, we get home and also get to work as safely as possible every single day. So by knowing the risk level in a certain area, it helps us achieve that goal quickly and efficiently. And this will lead us into the next slide, which is the Operational Route Service, also known as the ORS for short. This combines 3 aspects to create an overall risk, and those aspects are rainfall, recorded every 3 hours and 24 hours, asset vulnerability, and network criticality. Next slide, please. To make sure that the ORS risk level is as accurate as possible, we need to make sure that for each of the aspects, they are recorded to a high level. I'll just wait a second.
Sorry about that, Lilian. I just reached out.
No, it's okay.
Just slideshow again and then from current slide.
Is that better?
Click on the slide you were at. Double click on.
Yeah, I think the button comes up there, resume slideshow. There's a little pop-up window there.
Is that what's upset now?
Possibly.
Yeah, that's great. Yep. So, in order to make sure that the readings are as accurate as possible, for rainfall, this happens in 4 stages. The first stage is to make sure that the Network Rail Weather System, or the NRWS for short, is capable for reading and accepting thunderstorm alerts. This is because, due to the previous slide, you could see that when thunderstorms happened, that was when the heaviest rainfall occurs, and it coincides with when failures of our earthworks happens. Then we have to train our staff on the NRWS so that they know what to expect if, say, a thunderstorm alert does occur. Then we have to also advance the CAT and implement any agreed upon changes and improvements to make sure that our rainfall readings are as accurate as possible. Next slide, please. Now for asset vulnerability, to make it as accurate as possible, it is all to do with setting boundaries. So this means that we need to define what threat levels are necessary for the weather and also for infrastructure risks. Then when we've defined those thresholds, we outline them, and then we calculate an earthworks risk score for the root sections, and then link that to the said thresholds for an operational root section. Next slide, please. And with the asset vulnerability, is also linked to the network criticality. And with network criticality, to be reliable, it all comes down to communication. So to have good communication, we need to implement a method to deploy the earthwork risk scores as fast as possible. And that is done by using the global system for mobile communications, which is also known as using a satellite phone. And then we can also define 5-mile sections, and we can say which signals are within those sections so we know what could possibly happen in an area. Then finally, to make it very accurate, we need to develop an accurate weather response using GSMR messaging broadcasts to deploy those risk scores. And using those risk scores with the data from the rainfall combined together, it creates the ORS, overall risk score. Next slide, please. So now we know how the ORS works. You're probably wondering, what does it do? Well, it identifies which lines have high to low risk ratings. And by knowing the risk, resources can be allocated efficiently in those areas to solve the risk, as well as reduce the risk level, therefore changing, say, a high risk zone into a medium or even a low risk zone. It can also be used to figure out why a certain earthwork is failing. Usually it is to do with the drainage in the area, but there can be other reasons as well. Next slide, please. So during my business familiarization placement, I joined the final stages of this project, and my task was to create a spreadsheet which highlighted the risk levels of common travel routes. And I did this by highlighting various stations and also using the signal locations to find accurate starting and finishing points. The diagram that you see on your screens right now is an example of the data I would have to use. So if I was looking at a route that traveled through Bournemouth, I would have to use the Bournemouth measurement, which is 108 miles and 2 chains, and state whether that would be the start point or an end point of certain journeys. Next slide, please. I then got to use my own judgment to state the risk levels of certain travel routes. And this task was done for the Wessex region, the Sussex region, and the Kent region, which happens to be highlighted as the turquoise area on the map of Britain that you can see. I also got to make a manual to show others how to complete this for all the other regions that Network Rail operates in. As the end goal is to have an ORS spreadsheet for all Network Rail routes and regions. This way it will be easier for track engineers and also civil and building engineers to see where we need to spend most of our resources to make sure that our lines are safe. Next slide, please. So you're probably wondering, what are the main benefits to using ORS? Well, there are multiple benefits, and here are a few of them. We get to locate areas within regions that are prone to failure. We can spend and focus resources in that area to reduce those risks, as well as plan for failures that could happen soon. We can also get to notify councils about the risk levels of a nearby line, as well as help plan for reduced services and delays, which will be very beneficial as we can tell travellers about which trains might not be running, as that is one of the common issues we face if you ever travel. You go to the train station and you find out that your train is cancelled. And also, these notifications can help with the company reputation as well. Next slide, please. So you're probably wondering what the biggest benefit is. And the biggest benefit is that it's giving Network Rail a chance to learn from our mistakes, as well as ensuring us as a company and others around the world, they can learn from our mistakes, as well as make sure that they're not replicated again in the future. And thank you so much for listening to my part of the presentation. And I'm going to hand over to Fahad.
Thank you very much, Lilian. My name is Fahad Munir. I'm just like Lilian, I am a civil engineering graduate working for Network Rail, and I will be presenting today on soil moisture deficit, and I'll be explaining the causes for it, the effects of it, how we maintain it, and how we the management plan. So soil moisture deficit is where in the southeast region we have a lot of ideology with clay and dotted. Can I just stop right there? Lynn, I can't actually see my notes on my presentation.
Sorry, yeah, that's because are you only on one screen now, or are you on both?
I'm on one screen.
Yes. We might need to try that two-screen format. Otherwise, you're not going to be able to see them.
I'm really sorry.
Sorry, guys, just bear with us a minute.
Yes. Now I can see my.
Yeah, so we're only seeing your slide bank. So can you see your notes on your other screen?
No, I'm just putting it up now. Can you see my presentation? Oh.
We can. Can you just share it? Can you do resume slideshow on that little drop down, just so we can see the entire slide, or will you not see your notes if that happens?
The thing is, I don't know if I'm going to see my notes. I can maybe do that if that's better.
Yeah, if that works for you, that's absolutely fine for us. Fahad, no problem.
All right. Sorry about that. It just kind of put me off because I had.
Didn't mean to
sorry
catch you
about
out.
that, everybody. I'm really sorry about that.
No problem. Crack on.
So climate change projections suggest that we have periods with increasing average and maximum daily temperatures. This leads to drier summers, wetter winters, sea levels rising, and increased storminess. Increased storminess and winter rainfall will increase the risk of flooding, whereas heat causes soil desiccation and track buckling. Dry weather affects the settlement of clay embankments. This is caused by shrinkage of clay as the moisture is drawn from the clay. The moisture is further reduced if large thirsty trees are present. This process is which wet soils dry and soil moisture content decreases as the moisture evaporates into the surrounding environment, leading ultimately to affecting the ground surface. The problem we have is the ideology in the southeast is a mixture of clay, chalk, and a bit of sandstone dotted around. So the location of the clay are very susceptible to moisture change, and when they change, they are also sustainable to volume change. So when clay gets wet, it expands, and when it dries, it shrinks. This is determined by its plasticity. So a lot of our embankments through the southeast area are very susceptible to shrink or effect of the dry and wet weather when we get down here. Also, when you get this location coinciding with trees and vegetation, this causes the soil moisture deficit to increase. So what is soil moisture deficit? soil moisture deficit is the amount of water needed to saturate the soil and is the measure used to calculate bank settlement status. The most prone to essential settlement are those constructed with London, Liège, Galt and Oxford clays. The different settlement results in track geometry deterioration that requires expensive justification work to maintain a safe track and can result in operationally destructive speed restrictions. Now, during dry weather, the soil moisture deficit, which is the amount of water needed to saturate the soil, increases. This causes embankments made of clay to settle and results in a sudden deterioration in track geometry. The southern region has approximately 100 miles of these over-consolidated clay embankments. Now, soil moisture can have significant impacts within the rail sector. The occurrence of earthworks have been shown to correspond with ground soil saturation and weather conditions, which have been reported at the time of failure. This graph highlights the correlation between SMD against rainfall. It also shows the main hotspots for desiccation to occur. This dry weather, the way dry weather affects the soil is because, as I stated before, the clay shrinks when it's under heat or when it's like, for example, summer time. So because of that, it causes a lot of cyclic top, and it causes unevenness of the earthworks, which could result to derailment. It could result to the rail being actually uneven, and we have had previous experiences of the cyclic top, which is basically where the ground is uneven and the trains can't be traveling on the railway. Now, the impacts it has on earthworks is that the removal of water from the pore spaces in sandy soils does not affect the volume of the soil, but in clays, the removal of water held between the individual mineral components causes the clay to shrink. The amount of shrinkage is proportional to the percentage of clay particles in a soil, and clays with smaller particle sizes experience greater volume change. Now, drying effects caused by moisture abstraction by root systems are referred to as tree root desiccation, and the effects can extend to more than 4 meters below ground level and to considerable distances from the trees responsible. The images shown illustrate the impact of the track. Tree desiccation appear to only significantly influence track quality where the railway is at grade or embankment level. The impacts may particularly be emphasized at the interface between hard structures such as under bridges and earthworks. The impacts show themselves as the settlement, the track formation leading to isolated loss of track alignment. These defects commonly lead to bump reports and in extreme cases may require the imposition of speed restrictions to manage safety risks and associated with track faults. Once the impact of desiccation shrinkage start to show, the evidence is that movement continues for weeks, even after the trees responsible have been removed. Because of this lag time, early identification of accessible locations and advanced planning of interventions are essential. Now, the severity of SMD varies each year, but it is predicted that the very dry SMD peaks will become more frequent and longer. Previous experience has shown that track quality is adversely affected once the SMD rises above 175 millimeters. In the past 12 years, this has occurred in 10 years. Here is a diagram showing the average SMD by month for the last 12 years. Also, it shows the amount of TSRs that were instigated as a result. Now, as you can see from this graph, that the maximum, if anything greater than 200, we would consider that as high SMD and dry basically, and anything between 50 to 200 we consider that as normal, and anything between 1 to 50 we consider that as wet. Now, as you can see in 2018 and 2020, that the SMD levels were very high. We are still trying to figure out what the reasoning behind that was, as it's more recent than before. It's been the highest it has been so far, but that is basically caused by the weather. Now, these are the effects of desiccation on track geometry. As you can see, that it's had a lot of track quality problems due to the gaunt clay embankments, and track quality over time on the non-clay embankments shows that it hasn't had much problems, which is at the bottom, and the track quality over time on gaunt clay embankments is at the top, which shows, as you can see, which shows a lot of issues with it. Now, this is a correlation between good and poor track geometry. It is just from 2009 to present time now. As you can see, it's very vast in results, and you can see that recently it's had a lot of poor track geometry. Now, the impact of SMD on track quality is determined by TTRs. Now, as you can see in P3, that that shows that it was poor track quality, and as you can see in P13, it shows that it had good track quality. Now, the way we manage the soil moisture deficit sites is using the prioritization tool described, and based on the knowledge of locations where poor track quality is identified during hot weather. Delivery unit maintenance teams should be able to more accurately establish a mitigation plan. The mitigation plan is split into two sections. Prior to on-site of higher SMD, which is mid-November to May, the preparatory process and activities to ensure the track and earthworks assets are in as robust a condition as possible. Then the second part of the mitigation plan is the high SMD season, which is between June to November. One can state that as the summertime. The process and activities for locations requiring recovery work, that's just for the summertime, as that's when it mainly occurs. So our main management process is to make sure before summer occurs, we have all these mitigation plans into play. Now, the management of soil moisture deficit in terms of November to May shows that we review previous SMD season at risk list and actions. We review and analyze track quality and instigate maintenance intervention. We remove vegetation. We review historic deterioration rates to determine which sites are most likely to deteriorate again during the SMD season. We book ballast trains and tampers for SMD season and analyze of SMD effects on the track quality. The required preventative intervention and resources are recorded all on a shared drive. Now, the management of soil moisture deficit during June to November is we have weekly reviews of SMD Moric squares. We monitor sites using track quality information, camera and action accordingly. We intervene based on deterioration. We instigate weekly SMD coordination conference calls. We review weather for upcoming weeks, and we work with customers to ensure access is available to remove and keep off speed restrictions. And with that, I would like to conclude this presentation and pass over to Lee.
Lovely. Thanks for that, Fahad. Hi, everybody. My name's Lee Ratchford. I'm a civil design engineer with Engaged. Been with them for just over 4 years now. I'm going to present a talk on a track drainage issue. Next slide, please, Fahad. Next slide, please. There we go. So this is on the DSE line between Newton-le-Willows and Manchester. As you can see by the red circle there, about 60% of the site itself is in a cutting. It's a significant cutting of about 6 meters tall, significant slopes, with the tail end of the site itself on an embankment. Just look, the outfall to the site itself for the downside is right at the tail end of that embankment. Next slide, please. So the crux of the problem is right there itself in the picture. There's a significant flood issue on the site itself. This line itself comes within a primary or a secondary category, meaning that the track drainage itself is to cope with a 1 in 50 year design event as defined by the NR Drainage Design Manual. The site itself experiences multiple flood events a year to bottom a sleeper, with a couple of events hitting, as you can see there, the top of the rail. The main problem is this incurs significant delays, costs itself, and presents a risk to the track infrastructure. Next slide, please. So, believe it or not, track infrastructure is not a naturally occurring item. These were nice flat planes before the track came along. So one of the first things we look at before or during analysing the desktop information is what the existing flow patterns were on the soil and the ground around it, where the outfalls were, what incoming flows and runoffs were prior to the track essentially coming and installing a large gutter right through the area. Next slide, please. So as part of this, we identified up to 7 significant flows coming into along the track itself between a junction and the outfall. You'll see on the next slide that floors 1 and 2 were discounted due to them being outside of the remit site, as well as being dealt with by other track drainage. Floor 3 was defined as surface runoff from a field to the north. Floor 4 was a disused railway junction, which still had a slight dip in it, which was gathering water and discharging through redundant track drainage into this site. Floor 5 itself was defined as a ditch coming into the site from field runoff. That in itself was dealt with by siphons, and it was believed that the siphons themselves weren't functioning correctly. I'll just give Fahad a chance to catch up. There we go, yep. So floor 3, as we can see there, is between what's called Dolly's Bridge and Kenyon Tunnel. That was a significant flow which was gathered up by surface water runoff and then sent into the track drainage through pipes off-site. Number 4 is the track drainage. Number 5 is defined as the ditch, which was supposed to bypass the track infrastructure itself through a siphon. 6 and 7 weren't defined as quite significant, so they was combined into floors 5 as part of the drainage modelling that I undertook. Next slide, please. So part of the information gathering prior to the hydraulic modelling that we undertook was any desktop information that we could find, such as on the previous slides, analysing LiDAR data, finding where the flow runoff patterns are, any existing ground information that we can find, any existing network rail provided information that they have on the site itself. Part of the information gathering was a topographical survey through the site itself. Quite an extensive site. It covers about 3 kilometres, with the upside drainage outfalling about 2 kilometres down the track, and then the downside drainage running straight through to the outfall, which was a culvert that goes under the track and then off to the north. Ground investigation was undertaken through trial pits around structures and through boreholes themselves. Ground investigation found that there was quite a shallow bed of sandstone, which can become quite a design risk and constraint with regards to excavations. Part of the information gathering itself was catch pit inspections, manhole curves were produced. What this did was have a look at the condition of the catch pits, any visual siltation that's evident. The downside and the upside drainage themselves throughout the entire site, for the most part, was heavily silted. That itself lends a massive restriction on performance of the drainage. Third-party investigation was undertaken as well, field drain, siphons throughout the site, having a look at how the siphons are operating, whether or not they're functioning correctly, whether or not the flows into the site are actually being bypassed, or whether or not they're running down the embankment into the track drainage. Having a look at how much flows coming in off third-party lands, that's through visual inspections, even in dry nights, so there's still heavy flows coming into the site. Next slide, please. So throughout this works, we undertook hydraulic modelling. Hydraulic modelling in itself was produced through, the inflows were calculated and produced through two ways. One of them was ENA provided LiDAR data. What this does is you import LiDAR data into the model. This produces a mesh, which then takes the rainfall that you apply to it and then routes it into nearby drainage systems as it would work in real life. Incoming third-party flows, such as the field runoff, plus the siphons, plus third-party redundant track, that was produced as inflows, which is more or less point flows that get produced within the manholes and then flow into the system themselves. As you can see at the bottom there is a snippet out of the model. That snippet there shows surface flooding throughout the site. And because we experience surface flooding on site, we correlate the model itself, the hydraulic model that we produced, with what was experienced on site, and we can validate the model through that. And because the results themselves correlated to what we saw in reality, that validated the model. Next slide, please. If anybody can recognize that track drainage isn't that straight, that smooth, and it could be installed possibly a bit better. The ground itself, the ground profile, just take note, that is 1.8 kilometers of track drainage condensed horizontally. But what that does show is the ground levels through the site, on how you do, roughly at midway, you do get a dip through the site itself. An interesting bit of information was that the NR sectional appendix for this site stated that there is a very even 1 in 800 grade through the site. The topographical survey that we undertook, which measured all the rail levels, running edges, found that there was a dip in the site. The variance is about 1 in 750, which ties up with the ground levels. As you can see there, there's essentially a pond forming in the site. Next slide, please. The way that hydraulic modelling was undertaken, the rainfall itself was present in all the scenarios. The track drainage itself is designed to take the rainfall, and there's nothing you can feasibly do about that, so that was present in everything. The incoming inflow 3 was present for some simulations to test its sensitivity on how much impact that has, as was inflow 5 and inflow 4. They were toggled on and off to see how impactful they were on the results. Inflow 4 and 5 was assumed diverted. These are supposed to be dealt with by siphons, so the idea was that if the siphons were fixed, those would be diverted and the flows would be removed. Inflow 3, however, there was no feasible way to divert this flow, so attenuation for inflow 3 was modelled. Each of these scenarios, which was about 7 or 8 total, 8 scenarios total, was run at a 1 in 1 year event, 1 in 1 year rainfall and inflow event. If it passed, then it was ran over and over again for a 1 in 2, 1 in 5, 1 in 10, 20 and 50 until a failure is met. Next slide, please. that is a breakdown of the out scenarios. 1 to 7 is a combination of the existing inflow combinations with a track drainage relay rather, in either 450 or 600 pipes. And number 8 itself was if you did not deal with any external flows and the track drainage was to cope with all external flows, what drainage and what pipe size and grade was required to deal with that. If you could deal with everything external with an internal solution, what would that involve? Next slide, please. So to deal with everything internal, to deal with all external flows with just a track drainage renewal, that would require a 750 mil pipe on the upside and a 600 mil diameter pipe on the downside, and that would pass a 1 in 50 year event. However, 750 and 600 mil diameter pipes are significant. With the other scenarios themselves, saw little to no benefit without considering or managing external flows. The most significant flaw that we found during the modelling was the flaw in floor 3, which was the surface runoff from a nearby field, which was dealt with by, or modelled rather, controlled by attenuation. That yielded a result at 1 in 10 year, which is significantly lower than the 1 in 50 year requirement for the Network Rail Design Manual. Next slide, please. So there is a view of the extract of the hydraulic modelling. As you can see, some of the, that's the upside, some of the track drainage itself has been relayed and smoothed out with a 450 mil diameter pipe. This is with attenuation of inflow 3, which takes the flows, tanks them up, and then releases them into the track drainage in a slower, controlled manner. What you can see there through that water is the peak surcharge, or the peak water level throughout the rainfall event. Next slide, please. And likewise, there's the downside. The tail end of the site itself, that dip there, the drainage does run down the embankment. Next slide, please. So the conclusions were most scenarios, unless you deal with external third-party inflows, they fail a 1 in 1 year event with no significant benefit. To retain all the incoming flows and provide for a 1 in 50 year event to achieve the Network Rail Design Manual standard, significant pipe installations are required, such as a 750 mil diameter on the upside, 600 mil diameter on the downside. On the upside, this presents significant constraints due to there being a bridge to get through, bridge abutments to avoid. There is OLE on site, cabinets, electrical installations on site. So the most feasible option was to propose a solution that controlled third-party flows coming into the site through attenuation. This is proposed to have multiple benefits. The site itself holds an adverse weather site due to embankment slip. The drainage solution could have benefits to the earthworks due to bypassing or intercepting surface runoff, which is affecting earthwork stability. So currently, the proposal is to stage the works, deal with the track drainage, and then look at third-party solutions as well. And I think that is about it for that. So I'd like to hand over to Heather for the next part.
Good afternoon, everybody. My name is Heather Campbell, and I'm Assistant Project Engineer for Systems Engineering for Network Rail. I'm going to talk to you today and give you a little bit of an introduction to systems at Network Rail. Next slide, please. So I thought we'd start by just looking at actually what is a system. So a system is a combination of assets, equipment, people, procedures, software and data designed to work together for a common purpose. So one of the biggest systems that I know of is the railway, and it's a system that's made up of many different parts. So if you could just move on to the next slide. Oh. Thank you. Oh, next one. Thank you. Oh. Thank you. So the railway is a large system. Within it, there are numerous subsystems. So in the picture in front of you, there's a typical station commissioning with lots and lots of going on, but shows many systems that lie within the railway. For example, one of the systems within here is the signalling system. So I wondered if in the chat, some of you could pop in some subsystems that you think that you can see within this picture, or any that you know of within the railway. If you want to pop some in the chat, that would be great, just to see what you already know. Yeah, absolutely. OLE, the overhead lines is a system within the railway. Yeah, platforms, so stations, absolutely. Yeah. Have we got any more? Drainage, absolutely, yeah, very important one. Track, absolutely, yeah. So there's some really good suggestions. So there's many more within the railway that you can see, lots of systems. If we could just move on to the next slide. So yeah, so as we've seen in the chat, there's lots of subsystems within the railway. And within that, so if we take the signalling system, for example, that's a huge system. And within that, you've then got numerous subsystems, again, within signalling. So one example of that would be the power. So we need power to power many things within the railway, and specifically the signalling. So we have to have a system how that then connects with the national grid and all the power that comes from there as well. So there's multiple subsystems within subsystems, so it can become very complicated when we're looking at projects and maintenance. Just go on to the next slide, please. So once we've thought about all the different subsystems within the railway, we then have to think about all the interfaces. So when we're thinking about a project, when we think about or maintenance, we think about how this interfaces with the rest of the world, really. So when we think about Network Rail, we can then think about all the different interfaces outside of the company. So one of the biggest ones is our roads and highways. We interface with this in many different ways. So it may be bridges, it may be the passengers in their cars or passengers on our network, emergency services. We've also got our line side neighbours, our train operating companies and freight operators, and even government policies and funding. They're all things that are making an impact on how we run the railway as a system and how we have to respond when we're undertaking work. Next slide, please. So how do we approach this problem when we're considering a project? So what you can see in front of you is something that we call a context diagram. As you can see, it looks like a lot of things are going on there, but what we use this for, and we encourage every project to undertake at the very start of their project, is it's essentially a giant brainstorm of the entire project, of what you're aiming to do. So for example, in this project, Brent Cross, you put the project in the middle. It could be a project, it could be a task, whatever it is you're doing, pop that in the middle, and then start to so you get everyone the key players in a room, or you can sit down with them separately and start to think about the key players or key parts of the project that you're working on. So for example, if it was a track project, you may think, oh well, there's not many other disciplines, but when you start to think about, well, so if we're removing track, we need to then think about the track bed, we need to consider the OLE, we need to consider if it's at a station, is it part of a bigger program or project, is there station works going on at the same time, is there another project, for example HS2, is that going on at the same time, is that going to interfere with your project, is there a bridge nearby? Is the project going to interfere with the bridge at all? Is that going to then affect the highways? So these are all those individual things that when you start to put them down onto these context diagrams, and they can be displayed in a variety of different ways, this is just one example, you start to see all the different elements of a project, and then you can start to see all the individual problems that may happen or you may come across throughout the project, which sometimes you don't necessarily see until further down in the project. So by completing this, it just gives an overall view of what your project will consist of. Next slide, please. So we move on to something, so what do we do once we've done those context diagrams? Well, we look at requirements, which is probably something you're more familiar with. So if you could go back, please, sorry. So when we create requirements, it's really important to think about that context diagram and all the individual components that we've added in there all then have their own different requirements. So for example, the fire escapes, there may be policies and standards that you need to adhere to, diversity and inclusion, environment is something that every company now is bringing to the front, and that's something that we have to consider, and it affects every different element. So when we're talking about writing requirements and what the project requires, this helps to make sure that you cover every element of the project and each part, each interface involved. So how do we document this process? So next slide, please. At Network Rail, we have a requirements framework. This is how it currently stands at the moment. It's just about to be updated, but this is how it currently works at the moment. We're hoping to make it a little bit more simpler. But currently we have 3 different requirements documentation. So you start with a client requirement document, a CRD, which is a very high level document and often is sort of your remit. So it may say increase capacity by this much or this percentage, electrify this line to this line. So it can be very high level and could lead to lots of different answers depending on how you interpret the document. So we then move on to what's called a RRD, a route requirement document, which is project level, looking at sort of maintenance, what the route requires. It's a very medium level, not very detailed document. And then we move on to what would be a detailed route requirement document, so a DRRD. This is a project specific document. So this details all the things that you need to know when we talk about those interfaces and those specific requirements. So the lift needs to be this certain size, the bridge needs to be this size, we need to consider this standard, we need to make sure that we paint it this colour, for example. So this is where your requirements and that context diagrams and those interfaces that you've considered really come into play when we're writing these route requirement documents to ensure that we really hit the requirements properly so we actually achieve what we set out to do. Next slide, please. So how in systems engineering do we ensure that we actually, so we write all these requirements, we produce the documents, and then they get filed away. What do we actually then do with them? So as systems engineers, we undertake something called a verification and validation process. It's something that should go on throughout a project, but is often left right till the end and then becomes something that needs to get completed quickly. So we start with verification. So the point of this is to look at design. So your sort of grip stages 3 and 4, so your option selection and detailed design. And we're looking at does the design meet the requirements that we've set out? And if you're going through this at the actual time, you can then highlight issues that, oh, we haven't hit this requirement, we need to amend the design, which is much cheaper than trying to amend it further down the line. We then undertake a validation process during your further grip stages, construction and implementation. So this is ensuring that what is constructed actually also meets the requirements. So what we've asked to be done has actually been done, which sometimes on simple tasks seems really basic, but on giant projects, some of the smaller detail can definitely get lost. For example, we asked for this colour wall to be painted this colour, actually you painted it the wrong colour, and sometimes it might not matter, but it might be because we chose it to fit in with something else. So it's definitely really important that these are hit correctly. We ensure these are done by a variety of different ways, so it's done through either review or inspection or surveys or testing or demonstrations or analysis afterwards. Next slide, please. So at Network Rail, to introduce systems engineering and get it sort of more moving in Network Rail, they put together a framework called Systems Integration for Delivery, which is SI4D, and they highlighted 7 key themes that are really important to Network Rail and that we feel that we need to improve on. So the 7 themes are there in front of you, and these are things that we've brought in, things like the validation verification, the context diagrams, and there are lots of other different processes that have been brought in that we're trying to then integrate into project work to help ensure that we are helping to save money and we are doing what we actually want at the end. Next slide, please. So what is the benefit of systems integration? So we've got lots of different benefits there in front of you, but the key one is that we actually get it right the first time and every time. So when we've completed the project, we've completed what we set out to do. And it just helps, going through the processes with systems integration helps to have clarity on what's required from each of the teams, help people to be more effective in their role, and it's easier to confer with our suppliers throughout the process, and hopefully mean a better improved infrastructure performance and service for our passengers and our freight customers. Next slide, please. One of the biggest benefits of systems integration is cost saving. As I briefly mentioned earlier, finding a problem at the design stage and fixing it then is much cheaper than having to fix it at your implementation construction stage. So if you had to, if you noticed a lift, for example, wasn't big enough in the design stage to fit the right amount of people in, that could be amended at the design stage. However, if you had already installed the lift, then that would be a much more costly problem to fix. You'd either have to pull it out or find some mitigation, which would not only cost to fix, but then it would have ramifications on a programme, which could also have significant costs as well. The general rule of thumb is for each phase, so grip phase, for example, that a problem is left, the cost rises by a factor of 10, which is shown on this diagram in front of you. So the longer the problem is not seen, the more expensive it becomes. So systems integration, systems engineering, we're really trying to ensure that we've thought about everything to begin with, or as much as we possibly can, and we're just trying to help that on the projects, and then ultimately help to save money. So next slide, please. So thank you for listening, and I'll be happy to take any questions in the chat.
Thank you, Heather, and thank you all. Yeah, guys, if anybody's got any questions, feel free to ask them of the group or post them in the chat function, and I can answer them on your behalf. Dave's thrown a few in. Right, first one to Lilian. what is the data input into ORS?
I think the data input is to do with the rainfall data from the Met office, as well as the, I think it's mainly to do with the rainfall data from the Met office, and also the risk calculations are based off a matrix which is just the causation times by the likelihood. I think that answers your question. I'm sorry if it's not as detailed as you would like.
Thank you.
Fahad, I'm sorry.
Just saying thank you.
Fahad, there's one for you as well, and actually my question probably forms part of it. So Dave asks, do we need to chop all the trees down to mitigate soil moisture deficiency? But at the start, I wanted to ask a question of Lilian, but it's sort of merged into yours. What I'm very conscious of is we have a massive vegetation problem on the network. We often manage it in a way that I would call a scorched earth policy, where we literally take everything away. And that for me sort of introduces sort of earthwork problems or the potential for them. So my thoughts were, you know, what is the balance? What do we need planted that, you know, will sustain a bank for heavy rainfall, but wouldn't impact upon soil moisture deficit? So I guess that's probably a big question for either one of you, really.
I can maybe answer regarding in terms of SMD. What it is yeah, okay, we can, if that was an option of chopping down all the trees, yes, we can do that. But the thing is, in this day and age, we actually can't just get rid of all the vegetation, because in terms of environmental and you know, the standards and stuff like that, we can't really just chop down trees. But if that was possible, me personally, I don't think that I wouldn't agree with chopping the trees down, but it could help. But then you have to remember that SMD increases when the vegetation and the earthworks are, like, if the earthworks are dry and the vegetation is there as well, that adds onto it. But it's not just the root cause of SMD, the vegetation. I think the earthworks and geotechnical side of the SMD is the root cause of it. So because it's the fact that it's clay, and you know, clay shrinks and stuff, the reason it increases is because, yes, the moisture gets used by vegetation and stuff, yes, but the main cause, I think, is because of the formation of the actual geotechnical side of it. That's in terms of SMD. In terms of earthworks, I think Lilian might be able to answer that better than me.
So for the earthworks, like, I do remember asking my line manager about this for like a different project. When it comes to vegetation near the earthworks, it is okay to have trees, because trees, they do kind of act as like reinforcement bars. So they kind of like interlock and hold the soil. So you do not need to remove all of them, but it can become an issue, say, if the trees do grow to like a certain height, because usually how tall a tree is how long the roots tend to be. So I guess when it comes to a tree, you probably may have to prune them to make sure that they don't grow past, say, a certain length, so that certain height, so that the width of the roots doesn't affect the earth embankment too much.
Thank you. Question for you, Lee. Will managing third-party drainage be the key to railway drainage solutions in the future?
As for Kenyan drainage, this site in particular, absolutely. There's, to manage a third-party issue on track in this instance is very difficult. As for other sites, I suppose it could be on a case-by-case basis. I imagine each track drainage is designed to deal with the rainfall that it's subject to at the time. Given global warming and the increase on load on track drainage, that could be something that's more critical in future. To answer the question, I'd say yes. Cognizance can be made towards, increasing rainfall and increasing load on track drainage at the time of design. It cannot be given or not perfectly future prospects of infrastructure around the track. So to answer that, I'd say yes. Yeah.
Yeah, it makes me wonder whether we need to be working more with councils and so forth when they give planning permission. I know we've increased the fall in certain places just by new housing developments using track drainage as they get out, which is.
Yeah.
And one for yourself, Heather. Context diagrams, they look very complicated. Are they actually easy to produce and to interpret?
No, they're not. The example I showed was probably a more complicated one, just to show the breadth of different interfaces that can occur on a project, but that was a particularly large project. So no, they're not complicated to produce. They are more kind of like brainstorming sessions with the project team, and it's more just thinking about if you get every sort of discipline, project managers, sponsors, any third parties in the room, each of them is representing their interface, for example. So if you cover each one of those and just think about each part that they cover, you've built your sort of context diagram, just like you would a spider diagram, for example. And then what systems engineering or systems engineers do is we can help support the sessions. Network Rail, this is how it works. We support the sessions, lead them, or help to put them into a more coherent, pretty picture as such at the end. But the process isn't complicated. It's more about having the process of the conversation and thinking about all those important interfaces rather than necessarily the diagram at the end. I hope that helps.
Has anyone got any more questions?
Just thanks very much for the presentations. Bye.
Pete, on that note, can I hand over to you then?
Yeah, of course, Lynn. Just a quick one to start with. It'd be great if everyone could just take themselves off mute and give a round of applause to all four of our presenters who've all done a great job today. I'll just introduce myself really quickly. I won't talk for long. My name's Pete Fahad. I'm the chair of the Cheshire and North Wales PWI section. It's the first time we've done a talk like this with young professionals, and it's been really successful. Lilian, your presentation was a particularly pertinent subject to us, and one which I know has been in the public eye significantly, particularly with Stonehaven and Watford. It's actually rounded off our programme of presentations this year quite nicely, because one of our first presentations was from the RAIB, and Stonehaven was featured quite significantly in that. So it's really good to see what Network Rail are doing about it, and to get that update. So thanks for that. Fahad, a very interesting presentation from yourself. As a track engineer, I wasn't really clued up about soil moisture deficiency. It's a new concept for me, but it's a really interesting one, particularly the effect on track quality and how that varies for different types of embankment. And it's really interesting again to see how Network Rail are managing that. So thanks for that. Lee, a lot of people on this call, I think, are very familiar with the Chat Moss, pretty notorious area of railway to be working in and around. You probably remember We had a presentation about Earlstown a couple of miles down the track from there, and drainage did come up in conversation there as a bit of a sticky point, if you will. So from my perspective, it's fantastic to see a great piece of project work being done by yourselves just along the line to provide a new drainage system, and there's some great work gone into that, so thanks for that. And Heather, again, systems engineering, really interesting subjects and a really relevant one to all of us. From a project perspective, I completely agree with what you're saying about verification and validation, and it is something that is definitely not processed in the way it should be throughout the project cycle. It is pushed to the end. The use of context diagrams, again, I know Dave's asked about that in the chat. It's a really interesting one. I think it's going to be a really pertinent one to us in the Crewe area over the coming years, particularly with the Crewe Hub project. I'm thinking mainly because of the amount of interfacing projects that are happening in the area, with HS2. So, yeah, I think context diagrams are going to be something which I'll probably have a bit more sight of in the coming years. And again, yeah, fantastic presentation. So thanks very much for that. Just to round off the year, in effect, with a couple of comments from myself. And firstly, just a thanks to everybody, to all our presenters for the year, to everyone on the committee, to the PWI. The support that we've had from the team has been incredible, and has meant that we've been able to do a lot of successful presentations. So that's to Sarah, to Kate, and to everybody else. Also to everyone who is dialed into all of our presentations. We couldn't do it, and we wouldn't do it without everyone dialing in. So that's been fantastic. We've had a really big range of subjects this year, from adverse weather on drainage. That's one of the ones I've put down here, all the way through to kind of really technical things such as welding development. We've had a great attendance throughout, and as Lynn said earlier, it'll be fantastic to hopefully get back into our normal venue in Crewe in September. So just a quick plug, the next meeting is on the 2nd of September, which is a Thursday, and we've just organised that, and we think it's going to be design and construction of recent ballast projects, which is Barnaby Temple from Romberg Sursa. So that'll be an interesting one to some of the engineers based in Manchester, I imagine. I know we've had a few similar systems installed on projects there. So yeah, I think that's it from me as chair. Thanks again to everyone, and I hope everyone has a brilliant summer. Thanks very much.
Cheers, Peter. Thank you. I'll end the recording now.